Oh, what's up, SUPA class? Another day. Here we go. So today we're going to deal with electron affinities. We're going to continue with some of our trends. So our electron affinity is probably something you haven't talked about before. And it is the measure of the attraction or affinity of the atom for an added electron. So let me see if I can help explain this a little bit better. All right, so last class we talked about ionization energy. And ionization energy is really the measure of the energy change when electrons are lost. So for example, when Na becomes a cation and loses that one electron, its change in energy is equal to positive 496 kilojoules per mole. So to do this, energy is absorbed. That's what the plus sign means. So this is ionization energy. So electron affinity is kind of the opposite. It is the measure, it measures energy change when electrons are added. It really is kind of telling us whether electrons want to be gained or lost. So in this case, we want to know if sodium wants to gain an electron and become Na. Oops, that's not a plus, that's a -1. So our E energy of affinity, EA, for this would be equal to a negative 53 kilojoules per mole. That's what it actually is, right? And it's telling us that energy is released. So we can look at these electron affinities and we can decide if atoms want to gain or lose electrons. Right now we know that sodium doesn't want electrons. It wants to get rid of them. Right? So we're going to be able to compare these numbers and it's going to tell us something on the periodic table. So if you know the statement, you're in pretty good shape. The greater the attraction between the nucleus and the added electron, the greater the attraction between the nucleus and the added electron, the more negative the atom's electron affinity. So if our electron affinity, oops, that's not what I want. Is greater than 0. Okay, if the electron affinity is greater than 0, this means the ion has a higher energy, higher amount of energy than the atom before it gained an electron. So if an atom gains an electron and its electron affinity is greater than 0, that means the ion has more energy than the atom. Now remember, nature likes low energy. So it wants the one that has the lower energy. So if the atom has lower energy, then when it becomes an ion, which is what the electron affinity is telling us, okay, the ion is not stable. It will not spontaneously form. In other words, if that electron affinity is greater than 0, it will not gain electrons. So what's the trend of electron affinity? Okay, so let's start left to right. So when we look left to right, where's my out of curiosity here? So we're going to look. Let's look here. All right. So if we look at electron affinities going left to right, there really isn't a trend. This is across a period. There really is no trend. And here's why. It really depends on the electrons in the orbitals. So if we look at lithium and beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, and I want to look at their valence electrons. All right, so we're looking at the second PEL. All right, so for lithium, this would be my 2s orbital. It's got one electron in there. It potentially has room or would gain an electron to pair up with here, right? That's possible. Now, in reality, it's going to lose that electron, but there's room in this orbital for it to take. But if we look at beryllium, it's got an up and a down. For it to gain an electron, it would have to put it in the 2p's. And it definitely doesn't want to do that. It really doesn't want to do that. So its electron affinity ends up being greater than 0. Now, when we start getting into boron, now we're getting into those p orbitals. Px, Pyz, 2px, Py, Pz. And the boron has an up. There's room in here for electrons to be gained. Carbon's the same thing, because it would be here. Nitrogen ends up being a little bit different. Remember we said these half-filled p and d orbitals are relatively stable? Well, turns out that nitrogen doesn't really want to gain electrons very often, so it has an electron affinity greater than 0. As soon as we go on to oxygen and fluorine, again, it will start to tend to gain electrons. Now, neon is full. Okay. Its electron affinity is greater than 0. So going across the periods, all right, we have to look at their electron configurations really to figure out what's going to happen with their electron affinities, right? And there really is no trend. Now, what about top to bottom in a group? Well, turns out they don't change much. So there's a couple things that's happening as we go down the group. As we go down the group, the electrons added are in the same orbital. So there's a couple things that happens. So let's see here. How do I want to say this? Remember, we're adding an electron. How much does it want to add an electron? So as we go down the group, let's look at lithium and sodium. Right, so lithium has 2 in the first, 1 in the second. All right, and the electron is going to get added to this second PEL. And for sodium, it's going to go in the third. Okay, so we're always adding that electron to this outer PEL. All right, now notice Okay, so we got one electron in here and one electron in here, and as we go down, we always have that one valence electron. Right? So in here, there's a couple things that we're doing. When we add this electron, okay, if we add that electron, remember, this atom gets bigger. Okay, so the atom increases in size. If that's true, that means these electrons are going to have a less of attraction to the nucleus. Because it's further away. But a second thing also happens. Since the orbital gets bigger, okay, so since this orbital gets bigger because it's spread out, it reduces the electron repulsion. So these electrons are repulsed less. So we got two opposite things happening when we add this electron. And it turns out that these two changes balance out. And because they balance out, the affinity, electron affinity, does not change. All right. So in reality, you're going to be, you'll look up these numbers, all right, and you're going to, if it's really, really negative, it's going to want electrons. Okay, so if you remember, fluorine, okay, it wants electrons the most, right? It's going to have a big electron affinity. It wants electrons. But if we look over here and compare it to like some of the metals, they don't really want electrons, so their affinities are going to be much less, right? So it's really kind of telling us if they want to gain or lose electrons, right? And yeah, that's it, right? And most of we're going to look these up. That's about it. All right. So I just want to quickly run through, and I know we've talked about this before, characteristics of metals and nonmetals. Metals here, nonmetals here. So let's go through these real quick. Metals are lustrous. Okay, so most are silvery. Most have that silvery color. Most are solids at STP. They're malleable, which means they can be shaped. They're ductile, which means they can be drawn into wire. They're good conductors of heat and electricity. They tend to lose electrons to form positive ions. They form metal oxides. that are ionic solids. And if we dissolve them, they form basic solutions. Okay, and this is something that we'll talk a lot more in acids and bases, but it is a property of metals. Nonmetals, they're dull, and they come in various colors. They're brittle, so they will shatter. They're insulators. They do not conduct electricity well. These gain electrons to form anions. And then nonmetal oxides are molecular substances, and these will form acidic solutions. All right, so these are metallic and non-metallic characteristics. All right, so what are my trends? Well, let's talk about left to right. And it's pretty easy to see. So if we start left over here, what do we got? We got metals, 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 metalloids, nonmetals, and the noble gases. So these are metallic over here, and as we go across, the number of metallic characteristics are decreasing, decreasing, decreasing. The number of non-metallic characteristics are increasing, increasing, increasing. So it's pretty easy to see what's going on with metallic character and non-metallic character left to right. So metallic character decreases. Non-metallic characteristics increases. All right, and what's left to right? What's happening top to bottom? And it's actually easiest to see in group 15. Okay, so if we look at group 15, nitrogen, phosphorus, arsenic, antimony, and bismuth. Nitrogen is a nonmetal. This is a nonmetal. This is a metalloid, or actually both of these are metalloids. And finally, this is a metal. Okay. So as we're going down the group, we're starting with nonmetals. They're getting more and more and more metallic as we work down the group. Okay, so as we go top to bottom, metallic character increases. And our non-metallic character decreases. Now, that holds true in all of these. Now, these are all metals, I get it. All right, but what's the most metallic element? Well, it's francium. Okay, it's got the lowest ionization energy. Okay, it's extremely shiny. It's an excellent conductor of electricity. Right, so it's got all of these characteristics of a metal. Right, now that doesn't mean that lithium is not metallic. It's a very metallic element, but if you compare it to the group, it's the least metallic of all of these. Same thing on the other side. Fluorine. Fluorine has the most non-metallic characters. Okay, it's got high ionization energies. Okay, it wants to gain electrons the most. Okay, it is the most non-metallic character. Now all of these are non-metallic, all right? But when we compare them in a group, this has the most non-metallic. And these, as we go down the group, they become more and more metallic. All right. That's where we're going to stop for today. And yeah, we'll see you next class.